All right, so we are going to start our second round here of applications of derivatives. So we are going to do the next part. So we're going to talk about analysis, asymptotes, related rates, optimization, and linearization. So let's start with our analysis part. Whoops. So starting with analysis. Now, analysis is what we learned a long time ago in AB, Unit 3. That's where we did increase, decrease, relative max and min with the first derivative, and where we took the second derivative and did concavity in the POIs. So if I had a function, something like, I'll just make it x cubed minus 3x squared plus 1. All right, just looking at this problem. So if I wanted to find out where this thing was increasing, decreasing, and had relative max and mins, I would take the derivative. So that'd be 3x squared minus 6x. I would look for undefined, which there wouldn't be any undefined, and equal to 0. And I would factor this and solve, take out a 3x. If I take out a 3x, I'm left with x minus 2. So that means my two critical numbers are 0 and positive 2. And so that's where we did the table. And we did from negative infinity to infinity. And we put in here 0 and 2. And then we tested a number in each interval to decide whether the function was increasing or decreasing. And remember, to have a relative max, the function has to change from increase to decrease. And if it has a min, it has to change from the derivative has to change from negative to positive, which means the function's changing from decrease to increase. So hopefully you remember all that stuff about the first derivative. Now to do concavity, you do your second derivative. So our second derivative would be 6x minus 6. So I'd look for undefined and equal to 0. So of course that would be x is 1. So then if I did that for concavity, I would just have a table. I'd go from negative infinity to infinity, and I would only put 1 in the middle of it, and I would test in the second derivative something in each one to figure out whether we're concave up and concave down. And remember, if you have POIs, that's where your concavity changes. So anytime the function changes from concave up to down or vice versa, you have a POI there. So I know I went through that fast, but I think y'all probably remember doing that kind of stuff with all the tables and testing a number and deciding whether you're increase, decreasing using the first derivative, which gives you relative max and mins, or whether you have the second derivative and you're doing the concavity and doing POIs. So I didn't think I needed to spend too much time on that one. All right. Something else we learned, these are all applications of your derivatives. So this one says example of doing asymptotes. Okay, say I wanted to find any vertical or horizontal asymptotes for this particular function. All right, so in order to find horizontal and vertical asymptotes, I need to find the derivative. So this is an example of having to do the derivative using implicit differentiation. So that would be 2x plus 2y dy dx, and then equals derivative 25 0. So I'd solve for the dy dx, and I'd move the 2x over, and then I would divide by 2y. So that gives me negative x over y. All right. Now, so if I want to know where I have vertical asymptotes, that's the denominator. All right, because a vertical asymptote has undefined slope. So that would be when the denominator is undefined. So that would be when y equals 0. So when y is 0, I'm going to have vertical asymptotes. So now how do I find the x coordinates for my vertical asymptotes? Well, I'm going to go back to the original equation, right? I'm going to go back to the original, and we're going to put in 0 for y. So that was going to give me x squared equals 25. So when you take the square root, you get positive negative 5. So that means there are two points where we have vertical asymptotes, and that's going to be at 5, 0 and negative 5, 0. So that's two places where we have vertical asymptotes. So now what about horizontal asymptotes? Well, horizontal asymptotes is where your slope or your derivative is 0. So that's where this is equal to 0, which is going to be the numerator. So that's going to be your negative x equal to 0, which just is x is 0. So how do I find the ordered pairs where I have horizontal asymptotes? Well, that's going to be going back to the original, putting in 0 for x. So then that would be y squared equals 25. So y is the square root of 25, which is positive negative 5. So in this case, I'd have 0, 5, and 0, negative 5. So I have horizontal asymptotes at those 2 points. So I did that all using calculus, but let's really think about what's going on here. We know what this picture is. This picture is a circle. All right, x squared plus y squared equals 25 is a circle with radius 5. So nothing but a circle. So where do we have vertical asymptotes? Well, we have, I'll change my little color here. We have a vertical asymptote on this side at negative 5, 0. We have a vertical asymptote on this side at 5, 0. And that's the 2 points we found. Then we have horizontal asymptotes at the top and the bottom. So we have a horizontal at 0, 5 and one at 0, negative 5, which were the 2 answers we found down here. So we did it with calculus, but also looking at it from a visual standpoint, you understand that that's why these answers came out this way. That's because this is a circle. So we have 2 vertical asymptotes and 2 horizontal asymptotes. So that's how you find vertical and horizontal. So vertical is setting the denominator equal to 0. Horizontal asymptotes is setting the numerator equal to 0, and that's using your derivative. Okay, these are all applications of the derivative. All right, the next application of a derivative is doing related rates. Okay, related rates. So I know y'all whining and crying right now, but let's think about this, related rates, okay? A spherical balloon is inflated with gas at a rate of 800 cubic centimeters a minute. How fast is the radius of the balloon increasing at the instance the radius is 30 centimeters? All right, so I have this balloon, right? And the spherical balloon is being inflated, so it's increasing at 800 cubic centimeters a minute. So that's going to be the change in my volume. So that's a dV dt. That's the change in my volume. Spherical is inflated at a rate. Okay, how fast is the radius? So we want to know how fast the radius is increasing at the instance that the radius is exactly 30 centimeters. So when we're 30 centimeters, we want to know how fast that radius, since we're inflating, we want to know how fast that radius is growing. All right, so if you remember these problems, we need to have our equation. So we're talking about volume here. So I need the volume of a sphere. So that's 4/3 pi r cubed. All right. So now we want to have dV dt. We want the change in the volume. So that's taking the derivative with respect to time. So I'm going to take this derivative, take the derivative of this equation, the volume of a sphere with respect to t. So this would be dV dt equals, and over here take the derivative. So multiply 3 to the front gives me 4 pi, drop a degree, r squared, and then I have to chain on because I'm taking the derivative with respect to time, so dr dt. So now once I've done that, all I do is plug in all my numbers. So the change in the volume, since we are blowing up the balloon, the volume is changing at a positive 800. If we were losing air, if this was deflating, it would be negative 800. All right, and then 4 pi radius squared, so the radius is 30, and we're trying to find dr dt, so that's the rate of change in the radius, so the change in the radius over time. All right, so the answer, if you wanted to be real quick about it, it's going to be 800 divided by all of this stuff, which 30 squared is 900, times 4 is 3,600, so that's 3,600 pi. So it's 800 divided by 3,600 pi, okay? And I can get rid of my zeros. So that's going to be 8 divided by 36 pi. You can even divide by 4. So that would be 2 over 9 pi because I divided by 4. All right, so you could do that, or you could use your calculator and you get a decimal equivalent for the answer. Just remember when you put it in the calculator that you don't do 2 divided by 9 times pi. You need to make sure you do 2 divided by the quantity of 9 pi. So you want to put this in parentheses, because if you just do 2 divided by 9 times pi, you're going to get the wrong answer. So 2 divided by the quantity, 9 pi, and then you get the correct answer. All right. So that is related rates in a nutshell. So every time you take whatever your formula is for the problem, whether you're doing the volume of a balloon, the area of a circle, whether you're doing a ladder problem that's involving the Pythagorean theorem. So whatever formula you have, you're going to take its derivative with respect to time, and then you throw in all your numbers. All right. Now your units on your answer is whatever the terms are in the answer. So since we're doing a dr dt, R is going to be in centimeters, time is going to be in minutes. So this answer here would be centimeters per minute would be what this answer would be in. So 2 divided by 9 pi centimeters a minute. All right, so that was related rates in a nutshell. All right, now this one is optimization. So how do we do optimization problems? Well, this is still all applications of your first derivative. So a farmer has 400 feet of fencing to enclose a rectangular pen next to an existing stone wall. So here's my stone wall, and we're going to put a pen against an existing stone wall. We have 400 feet of fencing to do that. All right, so I'm going to call my width X and my length Y. All right, it says the wall side needs no fence. Find the dimensions of the pig pen that will produce the largest possible area. So remember, with optimization problems, we're maximizing or minimizing something. So this is where I had you do your primary equation and then your secondary equation, and then you put them together, and then you took your derivative. And your primary equation is always what you're trying to optimize. So this says largest possible area. So our formula we're trying to optimize is the area of this pen. So the area is X times Y. All right. Then our secondary equation comes from any information they gave us in the problem. Well, here's the extra information they gave us. The farmer has 400 feet of fencing. So I know here that I have 400 feet of fencing to use to make this rectangular pen. So that means 2 x's, because there's one on the left and one on the right, 2 x's plus y has to equal 400 feet of fencing. So that's my secondary equation. So now I put them together so that I only have one letter. So now I'm going to put them together to get my equation. So I think I'll solve for y and make it 400 minus 2x. And now I'm going to replace the y up here. So now my area is x times the new y value, which is 400 minus 2x. All right, so I solved this equation for y, and then I replaced it up here, the 400 minus 2x in that spot right there. So that means my area then is 400x minus 2x squared. That's the equation from area. So to maximize this, this is where the calculus comes in. All that was algebra. All right, algebra 2 stuff right there. So now I'm going to do the calculus part. So to do the calculus part, we're going to optimize this. We're going to maximize it. Well, you use the derivative. So A prime equals the derivative of this would be 400, and I don't know why my pen is having a spasm. All right, 400 minus 4x. All right, so 400 minus 4x. Give me some more space so you're not spazzing out. All right, so A prime, the derivative of this is going to be 400 minus 4x. So now we set this equal to 0. Let me make it neater because I can't even read it myself. Oh, golly. All right, so we got 400x minus 2x squared. All right, so my derivative is going to be 400 minus 4x. And then I just set that equal to 0 and solve. So, of course, that's going to give me 400 equals 4x, and you divide by 4, x is 100. All right, so when x is 100, that's going to maximize this thing. So each width is going to be 100, what's our units? Feet. So each one is 100 feet. And the width here, since I know it's got 400 feet of fencing, that means the y has to be 200 feet. And the question was find the dimensions. So my dimensions are 100 by 200. That would be my answer. So my answer is my length is 200 feet and my width is 100 feet. So my dimensions are 100 by 200 feet. All right, so all I did was I found my primary equation, my secondary equation. I solved my secondary equation for one letter, substituted in, found the derivative. All right, and make sure I did it all right. Yep. I solved for x, which x was 100, so that meant 100 feet was my width and 200 is my length. And that's it for optimization problems. So optimization is where you got to figure out equations that go with the situation you're doing, take your derivative to find your answer. All right, and then the last one is linearization. So if you remember doing problems like this, how can we use differential equations to approximate what 3.03 to the fourth is? So instead of multiplying this out, 3.03 to the fourth power, multiplying that out 4 times, we can use calculus to help us figure it out. So this is using linearization, all right? So I'm gonna use differentials, which is make basically a tangent line. So what function do I have? So what's my function f of x? Well, my function is x to the fourth. All right, and then so what's the derivative of that? My derivative is 4x cubed. All right, now what number can I use to approximate that's really, really close to 3.03? Well, I'm going to use 3. Okay, so I'm going to do f of 3. F of 3 is going to be 3 to the fourth, which is 81. So that means I'm using the ordered pair 3, 81, because that's what 3 is raised to the fourth power. All right, so now I need my slope, just one derivative. I need my slope at 3 because I'm using 3, which is really close to this. So now I'm going to do 4 times 3 cubed. So that's 27 times 4, which is 108. So now I can write the equation of the tangent line. I can use this point, and of course we know that the derivative is our slope. So I'm going to write a tangent line using the point in the slope. So my tangent line is y minus my y coordinate, 81, equals my slope, 108, and then x minus my x coordinate, which is 3. So this is the equation of the tangent line through this point with a slope of 108. And it's the point on this curve, x to the fourth. That's at the point 381. The tangent line has a slope of 108. This is his equation. So isn't 3.03 really close to 3? So because it's so close, the answer I can get from the tangent line is going to be close enough to the actual answer for 3.03 to the fourth power if I use the tangent line. Because we know an x to the fourth equation looks like this. All right, that's x to the fourth. So wherever the point is for 381, wherever that is, probably over here, so I don't know. But wherever that is, that tangent line is really, really close. So even though I'm getting the answer on the tangent line, it's going to be really close to the actual answer on the curve. But I'm actually finding the y coordinate on the tangent line, but it's really close to the curve, really close. All right, so all we're going to do is we're going to substitute in 3.03. So I'm going to put that in there. So y minus 81 equals 108. 3.03 minus 3. So I'm just substituting it into the tangent line and figuring out the answer. So y minus 81 equals 108 times 0.03. So y minus 81 equals, well, 3 times this is 324, but with 2 decimal places, so that'll be 3.24. All right, and then I'm going to add 81. So the answer is 84.24. All right, so there's my answer. And I use the tangent line to approximate that answer. All right, and if you do 3.03 to the fourth power, it's going to be really, really close to 84.24 if you actually did it on a calculator. All righty, so that was it for all the different applications, well, at least the first half, because there's one more video where we talk about all the big theorems. So that's all of the analysis and algebraic applications of derivatives.